All right, this is our last just-in-time lecture over molecular orbital theory. We'll review the most often missed questions on the second period heteronuclear diatomics and resonance. This question was making sure you were paying attention to the language. We switched gears here. Now we're looking at heteronuclear diatomics, which means that the elements differ. Okay, hetero means different. And so which one is not a second period heteronuclear diatomic molecule? Well, it's O2. I threw its MO diagram in here for comparison, though. Which theory predicts nitrogen monoxide, NO, to have a radical or unpaired electron? Doesn't matter what theory you're looking at, we see that the nitrogen atom is coming in with 5 valence electrons, as we see here. And oxygen is coming in with 6 valence electrons. 5 plus 6 is going to give you 11 electrons to place. And so we see those coming in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we wind up with that lone radical electron. This is predicted by both Lewis and MO theory. All right, this question is asking about non-bonding electrons in the MO diagram. So we saw how hydrogen can make a bond with fluorine. When it does this, it only involves the 2px orbital of fluorine. And so that means that we have these 2pz and 2py orbitals that don't change at all. So essentially, I'm asking 3 questions in one here. The electrons, the non-bonding electrons, are they shared in the molecular orbital diagram? The answer is no. They just come over and hang out. You don't see any dotted lines where they're interacting with anything. Second question, do the electrons change energy? No, they do not. Notice this line just comes straight over. So, no. And do the electrons contribute to the bond order calculations? Because they are not shared, that tells us this is also a no. All right, so for all of those reasons, this is going to be the best answer. The electrons are unshared, do not change energy, and do not contribute to bond order calculations. All right, so taking a wide-angle view of HF, we saw that, in fact, the 2s atomic orbitals are also non-bonding. Remember, hydrogen's coming in with its 1s. Fluorine is coming in with 1s2, 2s2, 2p, 1, 2, 3, 4, 5. All right, and we said that only one of these 2p orbitals is involved in overlap with that hydrogen 1s. And the rest of these are going to be non-bonding. So the best answer here is B. The 2s orbital and 2 of the 2p orbitals are non-bonding. All right, last question. You guys did really good on this one. How does molecular orbital theory describe the resonance in ozone, O3? So we've got this O3 molecule, and we've got our good old-fashioned valence bond theory here. And then we've got our MO theory here. And MO theory shows that one bonding MO is shared over all 3 oxygens. That's how it describes this as having the same bond lengths. And we see that it's going to be less reactive than if it just had a double bond and a single bond that had no resonance. All right, so one bonding MO encompasses all 3 oxygen atoms.